Hi everybody. Today we're going to be looking at the particle nature of matter, which should be revision for most of you. It is on page 3-19 to 3-22, and basically this means we're looking at the behavior of matter. Okay, so when we are talking about matter, we need to realize that we're talking about things that we cannot necessarily see. So how do we know how particles can behave if we cannot see an atom or some molecules under a microscope? So this is a very good question. And the answer to this question is we don't actually know how they behave. However, what we've done is we've come up with a theory which can try to explain what we see. And we can use evidence to support ourselves. So in the end, we don't actually know if we're right, but it's the best guess that we have. So we're just going to teach you the best guess at the moment. Okay, so in your book, you've been asked to write down names of theories that you are aware of. So you've just been asked for 2, so please just write down 2 theories that pop in your head. Okay, so I hope that you guys have written down your 2 theories. Okay, so some theories that you could think of are the theory of evolution, or the Big Bang theory, or the flat earth theory, the theory of climate change, the theory of gravity, quantum theory, atomic theory, string theory, theory of relativity, or maybe the theory of the tectonic plates, and there's way more. So as long as you have 2 theories written down, you're good. Okay, so now the next question in your book says, well, how do these theories follow the idea of things that can't be seen? So I'm just going to take 2 from my list. So let's talk about the theory of evolution. Well, the theory of evolution attempts to explain how humans have evolved from different things in the past. So in other words, the things that we cannot see, well, that's the past, and we're trying to explain the past and how we got from the past to the present, and that is something we physically cannot see. Similarly, when we're talking about climate change. So this attempts to explain how our actions today will affect our futures and the quality of life that we will have tomorrow. So again, because we are trying to explain the future, which we cannot see, therefore we are explaining things, or trying to explain things, which we cannot see. So please bear in mind, theories don't necessarily need to be between time. It can be talking about things that we have not yet seen, so like for instance the Yeti in the previous page, or things we actually physically cannot see yet, like atoms and the atomic theory. Okay, so how does all of this relate to particles? Well, we know that atoms and molecules are called particles, and we know that these particles make up substances like elements, compounds, and mixtures. But what we don't know is, do they have a definite shape? How do these particles behave? Do they have a color? What exists between the particles? And this is a very interesting question. So what exists between atoms? Because it's not air, because air is made up of particles. So what exists between the air particles themselves? Think about it. Okay? Or for instance, why do they actually behave that they do in certain ways? So all of these questions make us scientists think about what is going on in the world around us, and this is what we try and theorize to come up with the solution. So let's talk about this, and I'm hopefully going to make you think a bit today. So we're going to do experiment 1, which we're talking about chalk. So chalk, when we speak about it, let's talk about its physical properties. We know that it's solid, we know that it's usually white, can come in different colors, it's quite brittle, it's got a low density, etc. Okay? So now I'd like you to think about it. Well, if we have this solid chalk, why do we observe what we observe in the video? Please make sure you write down these observations in your book. Okay? And you're writing it down on page 319. Okay, so let's talk about a few things. If the chalk was a solid, why did the ink move up the chalk? So, does the ink just move on the surface of the chalk? Or does it move within the chalk? So if I had to break the chalk in half, would there be ink on the inside? Aren't the particles in solid meant to be so tightly packed that it would be impossible for other particles to move in it? Well, clearly not. Maybe that there are spaces between the particles, and if the particles, say the ink, are small enough, they can squeeze through those spaces and actually move through a solid. So a solid is maybe not as solid as we think. Okay, so the second experiment, you guys can do this at home. So what you're going to do is you're going to spray a small amount of perfume onto a piece of paper so that a small little wet circle is present. You can also do this with nail polish remover. In other words, we just need a liquid that stinks and makes a smell. So what you're going to do, you're going to spray it onto that piece of paper, get that small circle, and then wait until you can smell it. So most of you guys have done this before. So why can we smell perfume before all of it has evaporated? If you go back to your piece of paper, you'll probably see there's still a bit of the wet circle there. So the reason being is because as it evaporates, it still has an odor. So in other words, we can still smell it. And therefore, we're not smelling the perfume that's on the wet circle, but we're actually smelling the perfume that has evaporated, which is now in the air and moving towards our nose. Okay, so we need to write that explanation down on 319. Cool. So let's go to the next experiment, dissolving. Before we do that, what is dissolving? So this is when you take a solid and you break it up into smaller pieces, which then spread through the liquid. So please note, we're not actually changing what they are, we're just making more space go between them. So we're breaking the particle up. Okay, so how can we speed this up? Well, we can add energy. And we can add energy by heating up the liquid. We already saw in the pressure section how this adds energy. We can also shake the liquid. By doing that, we're forcing the particles to break up. And we can stir the liquid, again forcing them to interact with each other, and this forces them to break up. Okay, so what we're going to do now is we're going to look at an experiment which is going to compare two substances. So, in the left corner, we have ammonium dichromate with the chemical formula NH42Cr2O7 and a mass of 252 grams per mole. We'll teach you all of those stuff in grade 10. Okay, and on the right-hand side, we have potassium permanganate with a chemical formula of KMnO4. Its mass is 158 grams per mole. Who is going to dissolve quicker. So let's watch and see. Okay, so here we go. 1, 2, 3. You can see the potassium permanganate is on the left-hand side and the ammonium dichromate is on the right-hand side. We know it's dissolved when you can no longer see the solid at the bottom. Also, as it dissolves, it will start to color the water in the color of the chemicals. Okay, so I think you can clearly see which one is going to win this battle. Okay, so after all of that, we saw that potassium permanganate, the purple one, was a smaller substance, so it took quicker to dissolve compared to the ammonium dichromate, which was the orange-yellow one, and that took longer to dissolve. Okay, previously we also said in order to get the dissolving process to go quicker, we needed to add energy. So let's look at that one. So if we look at the potassium permanganate, the hot water is on the right-hand side, cold water on the left-hand side, and you can see how the process of dissolving goes much quicker in warmer water than in colder water. And we can see this because the flask is filled with the purple liquid quicker than the other side. So now if we look at experiment 3 a little bit closer, I would like you to observe the motion of those particles. So when you look at the particles as they are left in the liquid, so I'm not talking about it when they fall into the liquid, but as they are in suspension in the liquid, I would like you to watch their motion. And you will see that their motion is quite random. Okay? It moves randomly, and that is because the particles are colliding with each other. As they collide with each other, they change direction. So this was explained by a guy with a surname of Brown, and he therefore called this type of motion Brownian motion. So please note that when we're talking about the motion of liquid particles, as well as gas particles, because you can see the same thing in smoke, we say that they move according to Brownian motion, which means randomly. Okay, so we're going to now look at the same experiment again, but now with fewer or with less potassium permanganate, and we'll see that effect of the Brownian motion. Again, we'll also compare temperature. Now I would like you to look at the lines made by the particles as they are trapped in suspension. You'll see that they are colliding. The hot water has more energy, so the collisions are more vigorous and the change is more random, where the cold water is low energy, so it's a bit more controlled. Also, something that you could have noticed in that experiment is the process of diffusion. So diffusion is the movement of a substance from a region of higher concentration to a region of lower concentration. So for instance, if we place the potassium permanganate at the bottom of the flask and we just left it, they would move, so the particles would move until the entire flask is evenly distributed with potassium permanganate and water. And this is because if there are more particles in the same region, so in other words, more concentrated, there will be more collisions. Because there's more collisions, they'll collide with the other particles randomly, spread out randomly, and more easily. Okay, the particles will continue to spread until equilibrium is reached, and that's an important word we need to remember. So it will continue to spread until equilibrium is reached, which means that it's evenly spread. And the way that we can get them to spread quicker, just like with dissolving, we can give the particles more energy, and if the particles are smaller, they will move faster. Okay, so you can see the process of diffusion illustrated here in your diagram, the same diagram that's in your book. Okay, now let's look at it in action. so now we're going to have another battle between hydrochloric acid, HCl, weighing in at 36.5 gram per moles, and ammonia, NH4, weighing in at 17 grams per mole. I want to know which one is going to win the diffusion battle. Let's watch and find out.
Into the right hand side of the tube, we put some cotton wool that's soaked with concentrated hydrochloric acid. And into the left hand side of the tube, we put some cotton wool that's soaked with concentrated ammonia.
Please note this is opposite to your book. The contents are swapped around. So your observation will be mirrored for your book.
As you can see, we get a ring of white ammonium chloride formed. The hydrochloric acid and the ammonia diffuse along the tube, and where they meet, we get the NH4Cl, the ammonium chloride. Because ammonia is lighter than hydrogen chloride, the ammonia gas diffuses quicker and further along the tube.
So let's explain our observation. The hydrochloric acid particles were heavier than the ammonia particles, so they didn't travel as far. They didn't diffuse as far. And we can see this because the product, which is ammonia chloride, formed closer to the hydrochloric acid than the ammonia. So therefore, the ammonia traveled further. Please make sure you filled in everything in your book and uploaded pages 319, 320, and 322, and upload these to Classroom. Enjoy the rest of your day. Goodbye.